Hello, I'm Ryan Thier. I will be presenting today on YOLO v3 and YOLO v4 convolutional neural networks. To start with, I will just start with a brief overview of the general features of convolutional neural networks for image analysis in general, noting their increasing interest in recent years, discuss architecture and functionality, and finally talk about classification and comparisons between different frameworks. Then we'll actually get into YOLO itself. You only look once, with an overview of the YOLO architecture, the specifics of versions 3 and 4 with their changes, advantages, and disadvantages. And then finally conclude with some examples from the literature utilizing these frameworks in real applications, including agriculture, autonomous vehicles, gesture recognition, and facial recognition. So first, start with convolutional neural networks in general. Convolutional neural networks are one of a subtype of many different types of artificial intelligence tools. These AI tools have varying degrees of complexity and different applications. On the simpler side, knowledge-based AI systems simply take a list of user-defined rules and apply them to select input data to produce an output. More advanced machine learning systems can be told to extract explicit features from given data sets, thereby learning to map input data and produce an output. And then finally, deep learning systems, which includes convolutional neural networks, and we'll get into exactly what makes a CNN, can be taught to extract many simple features and build complex relationships between them to identify specific phenomena in data subset. Convolutional neural networks are a subset of deep learning, which perform convolutions and other operations along the way. We'll get into this more later, but it makes them adept at processing images. Just to start off with, for some context, there's been quite the explosion in interest in both convolutional neural networks and the YOLO framework itself over the past year. As you can see in the chart shown here, with data taken from the Web of Science database, there's been explosive growth in published results for both convolutional neural networks in general, as well as YOLO framework papers. Both classes of papers have seen more than a 10x growth in publications per year since 2014, up past 24,000 for convolutional neural networks and over 100 for YOLO papers in 2022. This speaks both to the high power of these applications, in many cases the ability to classify live video feed in real time with only tens of milliseconds latency, as well as the wide variety of uses of these systems, from identifying microstructural features in TEM image data to classifying apples in real time, as we'll show at the end of the presentation with some examples. So just to start with a brief overview of convolutional neural networks in general, this just kind of shows from left to the right the feed of the input through the various layers, and then finally to the classification output. The image classification, object detection, and image processing are all possible depending on the system precisely used. Input image data is convoluted by passing a filter over the image and performing tensor multiplication. The data then may be pooled to reduce its size while retaining most of the accuracy. Then the feature is subsequently classified and a prediction of its nature is made. Whole image may be identified, the feature may be boxed, its outline may be masked, whatever the task is, depending on the system itself. Convolution step is a very critical core building block of convolutional neural networks. Here's a simple diagram showing a quantified representation of a pixelized input image multiplied by some applied filter, and then producing a subsequent output array. Color images read in three-dimensional tensors corresponding to the red, green, blue pixel information. The filter moves across the image, checking if a feature is present, and the input and filter are multiplied to produce an output called an activation or convolved feature. An activation function applied measures whether a feature is or is not what it's looking for, depending on the biases and weights determined during the training process and used to inform the model. Successive layers of convolution operations can stack the information received in prior layers. For example, in identifying a bicycle, each individual part of the bike identified, frame, the handlebars, the tires, and so forth, make up a lower level pattern in the neural network, which later combine to represent the overall pattern that is the bicycle being sought. A key second piece of the puzzle here is the pooling operation. Here you can see a sequence from the activation with a rectified linear function, where the most important information is preserved and the less important information is stripped away, followed by the pooling operation, which reduces the total amount of information. Pooling can also be referred to as downsampling. In short, it reduces the number of parameters in the input. Similar to a convolution, filter, which is sometimes also called a kernel, sweeps across the incoming array. It does not have any weights in contrast to convolution, but rather it aggregates or condenses large arrays of information into more compact ones. In the example above, activation strips out the negative values in the input, and then pooling extracts the largest quantity in each quadrant to produce an additional array. This process does lose some information, but it speeds up and simplifies later steps. Optimizing this pooling process is an important part of applying neural networks. Finally, classification. Here in this system, it shows a kind of a brief workflow showing in this simple case, classifying whether an input image contains a cat with a simple yes or no binary. Just prior to classification, the convoluted and pooled outputs are flattened down into one dimension, converting a multidimensional tensor into a one-dimensional array. Final layers of the network connect to all the previous activations in the prior layer, so-called fully connected layers. They classify based on the features extracted in the prior steps. Typically, final layers use a classification based on the prior activations, combining the various weights and biases to make a probability prediction from 0 to 1 as to whether an image or feature satisfies the necessary criterion to be identified as the sought-after object. Last thing before moving on to the YOLO models themselves is to just discuss a few important parameters that crop up in discussing some of these frameworks, namely the intersection over union, IOU ratio, and the mean average precision. So the intersection over union is a ratio describing how well the predicted bounding box that is eventually applied over a feature circumscribes an object relative to the ground truth box. Ground truth box is the so-called the ideal condition. You might think of it as something you might manually define during training, the reference value. A couple things to consider include precision, which is a measure of how well you can find true positives out of all positive predictions, and recall, which is a measure of how well you can find true positives out of all predictions. Low precision, high recall results in most positive features being identified, but false positives are prevalent. Low recall, high precision means positive features are largely correct, but some get missed. If multiple classes are present, for example, if cows, horses, and sheep are all separate classes being identified in pictures of farmyard scenes, then the mean average precision, so-called MAP, will calculate the average precision for each of the animals, in other words, the average precision for each class in the sample set, and then take the mean of all of those averages. This MAP can be used to compare different frameworks working on a given set of hardware and working through a given data set. So now we get into YOLO. You only look once. Here's just a brief diagram showing kind of the high-level process of how YOLO is applied. YOLO is an object detection algorithm that can operate in real time using the convolutional neural network techniques discussed above. It is called You Only Look Once because a single neural network predicts bounding boxes and class probabilities directly from full images in one evaluation. The network simultaneously predicts bounding boxes and class probabilities for those boxes, training on full images and directly optimizing detection performance. The image is divided into an S by S grid, predicting B bounding boxes and confidence scores for those boxes. Each box has 5 parameters: X, Y, W, H, and the confidence. X and Y are the center coordinates of the box relative to the grid cell, and width and height are predicted relative to the whole image. A confidence value reflects the intersection over union ratio discussed previously between the predicted and ground truth boxes for the final detection. Here's a bit more detailed view of the sequence of architecture in the original YOLO model. So moving from left to right through the convolutional layers, finally to the fully connected layers and out. Per the caption, the network has 24 convolutional layers, followed by 2 fully connected layers. Alternating 1 by 1 convolutional layers with 3 by 3 convolutional layers reduces the feature space from preceding layers. The final layer predicts both class probabilities as well as bounding box coordinates. The bounding box width and height are normalized to those of the image in order that both fall between 1 and 0. The final activation function is a linear function, but all prior activations use the rectified linear function shown in the top right of the screen up here. In other words, it just, for negative values, the slope is, or the output value is highly decreased. So now we'll get into the specifics of YOLO v3 and what was adapted in that over the initial iterations of YOLO, and then what the outcome of that is for the performance of the framework. So a series of small tune-ups and additions were made in v3 to improve the overall performance. Overall, YOLO v3 runs faster than other detection methods with comparable performance, as you can see in the above figure on the left, showing inference time, kind of a measure of performance or quickness on the x-axis, and then the COCO, average precision, where COCO is just kind of a common benchmark that's used to compare various neural network frameworks. And you can see in the starred items, for roughly the same precision, YOLO v3 is, in this case, faster than what they were comparing it to RetinaNet variations. V3 introduces so bounding box predictions, now 4 parameters with 4 coordinates per box and an objectness score evaluating how well the bounding box overlaps with the ground truth box. Classification is done by multi-label classification, i.e. each box may contain more than one class, which is helpful for complex data sets with overlapping labels. Possibly the largest change in YOLO v3, or the most significant one, is that it predicts boxes at 3 different scales. In other words, from the original pixel size of the image, say if that's 256 by 256, in subsequent steps, it will downsample into kind of coarser arrays, getting more meaningful information from the upsampled features and finer grained information from the first largest feature maps, which helps with detecting features of disparate sizes, small versus medium versus large, compared to the original image. Additionally, the feature extractor now has 53 convolutional layers, which is shown in the chart on the right here, compared to the original 19. This is the so-called DarkNet 53 backbone. It's much more powerful, but still efficient, performing comparably to other frameworks like ResNet, but much more computationally efficient. YOLO v3 is very popular, but it does have some disadvantages. So in this table, the AP values along the top of the screen indicate various average precision measurements. And on the rightmost section, the S, M, and L subscripts refer to small, medium, and large, respectively. So you can see here I've highlighted a couple values for YOLO v2 and YOLO v3 compared to some other neural nets. And you can see that particularly for small features, the YOLO frameworks are much less accurate than some of the comparable frameworks. However, the authors note that while it is much worse, in this case, YOLO v3 compared to, say, RetinaNet is about 3 times faster. So which is better depends on your specific use case conditions. And v3 was a large upgrade from v2 in this respect. YOLO's primary advantage over other frameworks is its speed and efficiency, with some minor sacrifices in accuracy. These attributes apply to the training process too, meaning YOLO is ideal for cranking through large sample sets with lots of data. For example, traffic information or fruit separation, where you have lots and lots of samples to train on. In contrast, this makes it potentially less suited for smaller data sets or niche models where every bit of accuracy is necessary. YOLO v4, I guess I should take a step back here and just mention that YOLO versions 1 through 3 were created by a researcher at the University of Washington, Joseph Redman, who actually stopped working on YOLO after v3 due to his concerns about the potential surveillance and military applications of the work. After that, because all of this is relatively out in the open, an individual named Alexei Bachovsky proceeded to continue to work on YOLO v3 with some other collaborators and make an updated version called YOLO v4. I just thought it was interesting here, so I included this post I had found from the original creator, basically confirming that it's out in the world now. It's out of his hands. And this also stood out to me because I think the original YOLO paper has something like 7,000 citations at this point, and there is evidently an explosion of private companies trying to cash in on this very exciting technology. So it was striking to me that he would walk away from all that on somewhat of a moral standpoint. So I wanted to make a note of it. Back to the differences and the kind of under the hood, so to speak, for YOLO v4. YOLO v4 modifies a number of aspects of YOLO v3 with an effort to improve accuracy without sacrificing performance. So here is shown as kind of a rough high-level process flow for YOLO v4, including the addition of a sparse prediction pass-through, which is aggregated at the end of the process alongside the convoluted layers result. So the sparse pass-through takes layers before being convoluted and passes them to the end of the process where they are aggregated to the standard convoluted layers. And there's a couple of other additions to this framework as well, the so-called bag of freebies and the also equally fun named bag of specials. The bag of freebies refers to several offline training modifications that improve model accuracy. This includes things like data augmentation, increasing the variability and number of input images so the detection model has higher robustness for images from different environments. The bag of specials refers to plugin modules that increase the inference cost by a small amount, but significantly improve accuracy. This can include plugin modules that strengthen feature integration or screen model prediction results before the full execution of the network has completed. In comparison, YOLO v4 achieved pretty significant improvements over v3. You can see here that saw a very large, for a given FPS, frames per second, throughput here. So this blue curve this corresponds to video feeds in real time. The significant increase in average precision for a given FPS value between YOLO v3 and YOLO v4. This is a pretty significant leap, just from a cursory glance that I took. Subsequent versions, i.e. YOLO v7, had a much kind of smaller incremental increase in average precision relative to their prior versions. So this is a pretty significant step overall in the evolution of the YOLO framework. Now we'll get into sharing some examples from the literature that have made use of these frameworks and some real practical examples, and especially highlighting some of the strengths of the YOLO framework compared to some other frameworks. So the first example is for apple detection during different growth stages in orchards using an improved YOLO v3 identification model. So as the authors note here, real-time detection of apples is really important for judging growth stages and estimating yield. Here, YOLO v3 was used to detect apples during different growth stages with different illumination, backgrounds, and ambient conditions. You can see in this figure here, the similar kind of stock flow path that I showed at the very beginning of the presentation here is actually being applied to the researcher's subject, in this case, apples. They expanded the input data set by augmenting the original images with rotation, color balance adjustments, and blurring the images. And here you can see the results in that they've got pretty good intersection over union ratios for basically each type of apple that they defined here in various stages of growth between young, expanding, and ripe. They concluded that YOLO v3 was superior to the faster RCNN and VGG16 convolutional neural networks, which they said that at the time VGG16 was the state-of-the-art fruit detection model. And we're excited about taking next steps to apply these results to yield estimation and other practical things. Another application of this is in surroundings identification for autonomous driving. Here, of course, false positives in autonomous driving applications can lead to fatal accidents and horrible destruction. So increasing accuracy while preserving detection rate is crucial for this application. Here, the researchers modified the YOLO v3 loss function to improve the average precision. And you can see here, the top row of images is using kind of the stock YOLO v3 package, whereas the bottom row of images uses their modified loss function. And you can see in many of these, for example, the bus here on the right, their modified version really tightens up the bounding criteria of the boundary box for each thing in the identified classes. Similarly with this truck too, you can see it's kind of hanging off here, but they've got it very tightly described here. And it was concluded that YOLO v3, their modified algorithm that is, was the most suitable at the time for autonomous driving applications. Next, there was these researchers were working on gesture recognition systems, which can have a wide variety of uses, including but not limited to virtual reality and augmented reality technologies, assisted living, cognitive development assessment, as well as industrial applications like human-robot interactions in manufacturing and control of autonomous cars. So in this paper, they adapted YOLO v3 to develop a framework for picking up in real time hand gestures. The figure on the top here shows relatively high degree of accuracy that they were able to achieve. And the bottom left shows some examples of here where 1, 2, 3, 4, and 5 refer to the number of digits that the framework is observing that the hand is holding up. Finally, the last example I have is regarding face mask detection using YOLO v3. So the benefits of wearing masks to prevent COVID-19 are widely known at this point. So there's some interest in being able to determine who or what proportion of people in a space are wearing masks in real time. So the figure on the right here shows some examples of facial analysis with determining whether or not someone is wearing a mask or not. And these researchers compared YOLO v3 to faster R-CNN in order to achieve this task. The authors trained both models on a data set consisting of the same images of people with and without masks, and arrived at the results shown below. So you can see that YOLO v3 had a slightly lower average precision than the faster R-CNN model, but with the much faster inference time of YOLO v3, the authors concluded for real-time recognition of this kind of data set, that faster response made YOLO 3 the superior choice for this case. Yeah, so in conclusion, I've gone over some of the results or the basics of convolutional neural networks and the specifics of YOLO versions 3 and 4 relative to the original deployment and architecture of that framework, and then shown some examples that it definitely seems to me that YOLO is only becoming more popular. And I think YOLO v7 at the most cutting edge at this point is continuing to make improvements on the results shown here. And with that, these are the references I used in assembling this, and that concludes my presentation.
Okay. Well, I have some questions here. So if I give you an image that contains helium bubbles, so you can you point out on those images, and they are getting trained for YOLO, that means you are annotating a box around it when you start training it. And I have some output where boxes are there on the voids, and some of the boxes are not at the right position. Can you point out in the image what are true positive, false positive, true negative, and false negative in case of YOLO?
Just on any of the sample sets I
Yeah, any sample, even you can use one of your images. But this is slightly, this is in yellow, this slightly tricky.
I think I mean, most of my references here were, I mean, most of the papers I picked, the authors shared successful applications rather than failed ones. But false positive. So a true positive is correctly finding the right thing.
Right.
A false positive would be identifying something that is, or identifying something as belonging to a class when it doesn't in fact belong to that class. So for example, in this image, if there was two classes, taxis and buses, and this box was marked as the bus class, that would be a false positive. But then a true negative would be missing correctly not identifying a feature as a belonging to the given class, whereas a false negative would be missing something that truly belongs to that class. So in this case, there would be a box around, or if there was no box around this bus, that would be a false negative because there is a bus and they incorrectly identified it as a negative, not belonging to the bus class.
That means if it misses an object that was marked in your ground truth, right? If it misses an object that you marked in your ground truth, that would be classified as true negative, right? Makes sense, right?
Yeah.
Okay. So now this was slightly tricky because all these people get very confused. Okay, they know when they start training the model, they know this thing that if you're providing the box around an object, that's a true positive. If your model gives the box at the same place, so it's basically the intersection of the boxes that you provided with the ground truth. If there is one-to-one intersection, they all are true positive. And if there are extra boxes it has provided, they becomes false positive, all the extra boxes. Now coming to the negative class, as you told that if it has missed something, right, where it had to do, that will be your true negative.
Right.
And I think similarly applied for false negative. Okay, another quick question. From YOLO 1, you went also to YOLO V1. And YOLO V1 to YOLO V3. So in YOLO V1, the main change that you have a higher precision in YOLO V3, there is a concept of anchor boxes. Any comment on that? Because YOLO V1 doesn't use anchor boxes. And because of that, what was happening is if your grid has two objects, the center of two objects is present in a grid, then it doesn't know how to take it further. That's why they introduced the concept of anchor boxes, where they were, localize everything, and they were trying to do a regression with respect to the anchor boxes. Yeah.
I see. Yeah, I did read about them. Frankly, I didn't feel that I understood the distinction between anchor boxes and the ground truth boxes well enough to be able to speak to it, compared to some of the other distinctions that I picked up here. But yeah,
because my main concern was the MAP values that you showed, they become very high for V3, right? MAP value, the table of comparison that you provided
here.
I think in the conclusion, in the slide that you were comparing MAP values. Yes, here. So these were the MAP values where, it refers to small, medium, and large objects. And for small objects, so the main thing that we noted The biggest change was 5 to 18 for the smaller objects. Now, YOLO V3 started working very well for the smaller objects. And one of the reasons that we know is it started using 53 convolution layer. So it started taking the details of the tiny objects really nicely. So this was one thing. But what are the other things that we could talk about here that might have changed?
Well, I mean, you could also point to just the general 50% increase in average precision between V2 and V3. That is from 21.6 to 33 here.
Why do you think there's such a great improvement? What was changing in YOLO V3? You know, YOLO V1, V2, V3, they are very important version because there was a lot of change introduced within them. Like then V4, V5, V6, it's very little change. But from V1, for example, they had fully connected layers at the end. But in V2 and V3, they removed the fully connected layer, which is a big change because if you remember, a fully connected layer is a layer that consists of neurons. That means it does all kind of probability calculation. That means an image, it is flattened into a matrix and then is entering into fully connected layer. So after max pooling, everything that we do, it's flattened into one dimension. And then it is getting into the neurons, right? However, in V2 and V3, they removed the fully connected layer. So I wasn't, it was very interesting to read that how in that case, it is still doing the classification. Because classification is mainly done, on the probability basis, right? It thinks the algorithm, it finds its nearest neighbor while training and then tries to compute the probability based on that. So any idea on that? Like V2 removed the fully connected layer. V2 also introduces the concept of anchor boxes. It used the darknet. Then what started happening in V2 was it started doing the classification and detection at every scale, small, medium, and large. That's why we don't have V1, because V1, it does not provide that. V1 only does it at one scale. And that's why they were using the concept of bounding boxes rather than anchor boxes. So this was one addition here.
Sure.
Other than that, yours was YOLO V4, right? And what happens, how is the precision changes on V4?
Well, I tried to touch on that in,
Here, right?
let me see. In this slide, I had a relatively high level. I found the original, the actual paper published on YOLO V4, outlining it to its debut, so to speak, and I found it somewhat difficult to break apart, but I tried to include what I perceived to be the significant changes here.
Mm-hmm. Okay. Yeah, because these are a bag of freebies and a bag of specials are the main two changes that it has, right? Yeah. Okay. So we don't have the precision values for V4 here, right?
Just in this comparison that was published in that paper, but not tabulated.
Right. So if you see here, it's in frame per second. It's gone from 33 YOLO V3 versus 44. It's an MAP improved by 10%. Right.
Yep.
And any idea why we have this improvement? Like what's core changing? Because why this thing is important? Because, for example, I give you a data set and I give you a data set where you have a voids and you have a voids of all similar sizes, 10 nanometer, 10 nanometer, 10 nanometer. You don't worry, you don't care. You simply applied YOLO V when you're good. Now I give another data set to you in which you have a, what do you call as double population.
Bimodal.
Bimodal. That one, what happens is you have a smaller population and you have a bigger population. You have two different scales of the same object. Now you will start using V2 and V3. Now I give you another data set in which there is an, what are occluded objects? Occluded object is like one object is hidden behind the other. For example, if I hold a book here, my face is hidden behind it. In the same ways, in your microstructures, you have a void which is hidden behind another void. A lot of times you just don't see, the projection is overlapped.
Sure.
In that case, we use, a V4 and even higher version because they introduced more of the loss functions there. So that's why, depending on the data set we have, we use a particular version, and having this kind of comparison, it makes it a little bit easier. Easier to, take it a first step when you start analyzing your samples. Okay, but overall, good understanding and good presentation.
Thank you.